So my name's Jason Wodicka. I'm the lead developer on the team that's building Analytics 2 for Canvas. And so I'm here to talk about what we did and, more importantly, to talk about why. So I build software, so I could really talk about a lot of things. The things we did to make it faster, the things we did to make it work on old computers and browsers and not make mathematical errors, and a lot of software things. And I actually don't think that'd be very interesting or a good use of our time together. So I'm actually not going to talk about the stuff that I did the most, but instead I'm going to talk about stuff that the whole team worked on. So I really just want, before we begin, to make sure that I give a lot of credit to the designers, to the product people, and to all the other developers I worked with, because this was really a team effort, the stuff I'm going to show, and I'm about to talk about it like it was all mine. So now I'm going to talk about it like it's all mine. But really, I do hope, my goal here is that by seeing the stuff that we did when we worked with data, and understanding the principles behind it, you can use these same techniques when you need to understand data or communicate about data. And there's a bit of irony in this, because it's kind of silly for me that I'm up here talking about data, because I am not a numbers guy. I failed freshman calculus in college. I'm going to admit that in front of a room of educators. And that's not that abnormal, but I failed freshman calculus enough times that I had a master's degree when I passed freshman calculus. So I'm really bad with numbers, which is actually, I think, why I gravitated toward visualization, because I can't make them do the things I want in my head. So I've had to learn to make them do the things that I need to understand on the page so that then I can get the insight back into my head. And that's why I care about this, and I hope that everybody else here is going to care about it too. When I got started, I got a lot of advice from people, lots of free advice, worth what I paid for it, and a lot of it was contradictory. Always label data points with their values, I was told. I was also told, don't clutter your graph with duplicate information. There's a problem here. But everybody always gave me one piece of advice consistently. If it doesn't work, they're all just guidelines. Go with your gut. And that was really vexing for me, because I'm a computer programmer, and I'm reasonably certain that I'm not permitted to have instincts. That's not what I'm for. So I had to go looking for a better source of answers than my gut. And actually, I found a lot of those interesting answers in the other field that I ended up studying while I was busy failing calculus, which is cognitive science. So what I found is that some of the best models that we have for how we understand our thinking and our seeing the world, those models have implications for how we can represent data. So by grounding our designs for charts and other data visualization in that research, we can cut through some of those contradictory recommendations, and then we can find the underlying structures about thought, about perception, that are guiding those gut feelings about what works. And so we've used those in building the new analytics, and I'm going to show you how we did that. But more importantly, I hope I'm going to show you how you can do it too, because once I'd done the research, I was really surprised by how straightforward a lot of this can be. But straightforward does not mean simple, so I need to put a giant footnote on this talk. I am oversimplifying things a lot so that we can get through them in under 40 minutes, because this could fill the first 5 or 6 classes of a good college course, and I don't have that. So I'm going to refer to sources. I'm going to give you links at the end. You can follow up if you're interested. Anytime you see a URL or a title referenced, I promise you, there's a slide at the end that has all of them, so you just need to take a photo of that one. But my goal is to give you all the most important stuff here in this room, so if you do no research after coming out of this room, you can still put some of this stuff into practice. So if stuff here seems a little too easy to be true, or if you know the field and you're like, he is simplifying the heck out of that, yeah, I am. As the footnote says, it's more complicated than this. So let's dive into some data. So here, I've got some data. This is data from the Stanford Education Data Archive. So this is showing performance on a set of standardized tests across different schools. And here, let me show you some more of it. So this is the raw data from them. I've done nothing to make this data more comprehensible, but that is my point, because right now, like this, we have no hope of understanding this, and that was less than half of one state. We've got 47 more of them, because I think this is only the continental US. So we can't draw conclusions from this. We can't use this. But when we do this to it, this is that same data set charted on a map of the continental US. So now we can see things about the data without us really trying. We can see these big regions of green and purple, and we can't really unsee these. We would have a hard time telling our brains to stop seeing that. And so we could have a lot of conversations about this data, but the conversation I want to have is about how we can have that conversation now. What just happened here? This data just became comprehensible. I mean, In one sense, this is common sense, right? You took the data, you put it in a comprehensible form, and now it is comprehensible. But what about this form made this data comprehensible? And that was the question that I really wanted to go with, because there's a lot of other ways you could have represented this data. You could have done bar charts and scatter plots and all kinds of other things that would not have revealed the data the way that this map does. So I'm going to start by talking a bit then about the brain. And I'm going to start by summarizing way too much a book by a man named Daniel Kahneman called Thinking Fast and Slow, which in itself a summary of a whole lot of cognitive science research. And the broad idea here is that we've got two basic kinds of thinking systems. And Daniel calls them quite imaginatively, System 1 and System 2. So System 1 is the old system. We've had it for a long time from a sort of evolutionary historical perspective. It's involuntary, it's fast, it's all the decisions that we can make without thinking. So when we train up a task to the point where we can just do it without trying, without thinking about it, that's System 1. But then we've also got this System 2, which is much, much slower. Oh, and System 1, I like to call this the heuristic system, so you'll hear me say that a lot, just because memorizing 1 and 2, I said I'm bad with numbers. So I think this is the heuristic system. So System 2, on the other hand, System 2 is deliberate. It's much slower, but it's also more flexible. So this is the one when we think we're thinking, that's System 2. It's the one that feels like thinking. And it works through problems and tasks deliberately, logically, and most interestingly, System 2 is the one that can self-evaluate. System 2 has the feedback loop, and it can go and sort of look at the results of both systems and figure things out. But I really can't emphasize enough how much slower it is. This is a system that if we needed to use System 2 to decide whether to run from that oncoming train, about the time we'd be done with the decision, we'd also be splattered. So we're not going to be able to use this to survive. Neither of these systems is the good system. We need them both to do the things that we do, which is to think as humans really flexibly. So I want to give you a really concrete sense of how both these systems feel. Oh, and by the way, I call this system the cognitive system because that's what my advisor called it in grad school. So it stuck. But it is a good name. It's a good way of thinking about it. It's the one when we think in the cognition way, that's the system we're engaging. So let's talk, though, about learning to drive. Who here has learned to drive a car? For those of you who didn't raise your hand, I'm sorry, this example won't make as much sense. So when you learn to drive a car, for those of you who did, it requires all your focus, right? You have to think about everything. Which foot goes where on what pedal now? Am I putting on the wrong one? Am I about to accelerate into a wall? I bet you don't do that today. Today, it's really easy. Your feet go places, everything just works. And what's gone on is when you began, you were driving using System 2. You were using the cognitive thought to drive that car because you needed to. There was no heuristic built up for how to operate a motor vehicle. But over time, various parts of that task get moved to System 1. Knowing how to move your feet to operate the pedals, knowing how much shift on the wheel causes how much change in the environment. But, and this is essential, not all of it gets moved to System 1. If you drove here to Keystone, you probably went on some roads you've never been on before, and you were using System 2 quite a lot to find your way around, unless you had outsourced that thinking to Google and were letting it talk on your GPS device. When we use both systems in concert, we're basically going through daily life. But sometimes you can even end up going full System 1 when you're driving, particularly if you think about driving home on familiar roads. Who here has ever, lost a mile or two, taken a couple turns and been just like, I have no memory of doing any of that? System 1, straight up, the heuristic system, you have built up patterns for that entire drive, and you didn't need to engage the expensive, slow, did I mention expensive, System 2, so your brain was like, we can use that for other things, or even let it rest a little. Cool. So what's this got to do with data? Well, when we turned it from that pile of messy data into this map, we moved the processing of that data from System 2, where we had to think through every data element, to System 1, where automatic processes, these heuristic processes we've got, just naturally made sense of it. Now, something interesting here, I've talked about a bunch of processes with driving that you learned, heuristics that you learned in System 1, but not all of the thought processes that feel like System 1 processes are learned. Some of them are pretty fundamental, and the ones we're talking about today are pretty fundamental, so I don't want you to confuse that because it's a little confusing. Sorry. Now, I've been talking a lot about understanding data, but communicating is another big thing. So, this is a bunch of data, right? I mean, there's just a bunch of data there, and it's not really easy to make sense of. So I could tell you that there's a message in this data, and I could tell you how to find it, and you'd be able to find it, I promise. But we don't have time, so I'm just going to change how we're displaying the data and discover that this computer has totally reformatted my text, making it a little harder to read. Life goes on, but the data comes out. You can see it. And now the message is apparent to you, even though I did nothing to actually change the data. The data is all the same data. I just made some of it a little less visually obvious and some of it a little more visually obvious. So when we communicate about data, and I think a lot of us communicate about data, a lot of us need to talk about the data about how we're doing in our jobs, or the data about things that we're seeing that we're worried about, that we want other people to be worried about too, or things that we're not worried about, and we have data to say, we think this data says this is nothing to be worried about. When we communicate about those things, if we can use good visualization to ground that communication, we move the conversation from explaining what's there to talking about what it means. And that's a huge advantage in a world where the person you're talking about might not agree with you, and once you've got the data on the table, they might not believe you that it means what you say it means. Now you're to that discussion, instead of having a discussion of first getting them to even see the data that you see there. So I keep saying see, and this talk is called data visualization. There's a visual in there, and the reason is that all of this is quite literally built on how we see the world. We are basically, data visualization is exploiting the underlying structure of our visual system. So my first giant caveat here is there are ways to do this that are accessible to the blind, and I'm not going to talk about them at all because they are completely orthogonal, because this talk is all about how the visual processing system works and how to hack it. So to do this for somebody who's using a different sensory processing system, you'd need to look at the same research for that processing system. So this talk, though, is going to be focused on visual processing because most people have that as their dominant sense. We have a lot more sensory receptors on the eyes than we do anywhere else given, and I think actually full majority straight up. And we have some illusions about how our eyes work. It feels to us in the world like our eyes are just a camera. They're out there, everything's straight in front of us, we just see it, take in a perfect image that we can see all of at any moment. And of course, we know at some level that's an illusion, because when we see a desk, like if you actually focus in on one point, you're not seeing this, you're seeing something that's a lot more like this. Your field of vision is very, very precise near the center and gets very hazy out near the edges. We talk about peripheral vision. So how is it that from vision that works like that, we've got a sense right now, an unshakable sense, that I can see this room in full resolution. I believe that. I can see each one of you, the details of your face. Why do I have that? Why does my brain keep telling me that? Well, because our sight isn't actually much like a video camera. It's much more like this guy. This is a sports photographer at a football game, and he is moving that camera constantly. He's following the players with the camera, moving to all the interesting spots on the field, and taking the pictures through his very little field of view. And from that, you build up a sense from his photos of the whole game. And it's like you kind of knew the whole game because you saw all the important bits. Because assuming he was perfect, which our eyes kind of are, you saw all the stuff that really mattered. And when we think like this, we talk about this process as a process of active vision. And I'm going to take some active water here. It is really dry up here in the mountains. So I'm just going to give a quick visual example of how this feels. Because our visual field, it's kind of like this at the start, right? What we're seeing, except for that one little area, is all this very low resolution data. But then as soon as we start snapping in on areas, little pieces of it come into focus. And one of the things that we need to remember is that we also have memory. So, and we, in addition to what we think of as our short-term and our long-term memory, we have something called visual working memory, which is way shorter term, but totally unconscious to us. So as we start to move our eyes around, we just start building up all the little pieces we've got in our visual working memory without awareness of it, until eventually we've got a sense of the whole image, even though we've never really looked at all of it. So that confabulation of all of these little pieces into one thing is one of the coolest tricks our brain plays on us. And even though I have been knowing we've been doing this for years, I still can't stop myself from believing it's true, which is, again, tells you how good our brain is at tricking us. But, so there's something here that's a little weird, because If this is the case, then why don't our eyes just jump randomly to whatever random thing? Why don't we see rooms in random order? We tend to jump straight to the important stuff somehow, and how can we do that when what we're seeing is this? Well, the answer is that the only thing that's operating is not our conscious awareness of what we're seeing. A large chunk of our visual apparatus is operating below the level of thought quite automatically, and that apparatus is what I'm here to talk about now. So we talk about that process that puts our small point of attention somewhere as the process of attention. So these traits that we can pick out before we have focused our eye somewhere, we call them preattentive attributes because we can use them before we're paying attention. And so Anne Treisman did some research in the late 1980s, and it went like this. So she got herself, I am presuming some college freshmen because all psych research is carried out in college freshmen, and she basically gave them a screen, and she said, I'm going to flash in front of you for 1/10 of a second something with a whole bunch of shapes, and either they'll all be circles, or they'll all be circles and there'll be one triangle, and after I flash it, I want you to tell me whether there was a triangle in the set. Now, I can't really flash things in front of you for 100 milliseconds, and we don't want to do that anyway, so I'm just going to show the images here, and I promise there will always be one, but I want you to pay attention to how quickly your eyes can find it. So there's one triangle here. You saw it jumped right out. Now again, there's going to be one orange circle with all the blue. Now we can also do this, so we talk about the properties of the things, but we can also do with group properties. All the objects in this one will be the same, but one of them is going to be out of whack with the others. They're all going to be aligned, except for one of them. So see how fast you find that. And similarly, we can do the same thing, all the objects in the same position, but one's rotated differently. The angle is different. So just a couple more of these, because we could just basically make this all a little slideshow of psych experiments. Gray value is one that's really interesting, the brightness of something between 100% dark and 100% light. So this is a uniform 50% gray. I'm going to have a whole bunch of white circles on it and one black circle. That one, by the way, is invertible. If I'd done a whole bunch of black circles and one white circle, it would have worked. Not all of these are. Actually, all the ones I've showed you are. I'm sorry, I just lied. I cut out all the ones that are not fully invertible. If you do a whole bunch of like minuses and one plus, that jumps out. If you do a whole bunch of pluses and one minus, it doesn't. But cut that for time, sorry. So I'm going to show one more of these just because I want to be clear. Most of these have been static, and all but one of these are static because we're going to be talking about static charts. But not everything our visual system can process is static. So we've also got motion. So one of these dots will be wiggling, just a little. See how fast you find it. So why are these traits like this? Well, these traits are actually being processed as one of the first stages of our vision, well before the data has reached even some of the aggregating stages of our brain where it's coming together. We have dedicated neurons that are watching for things like this. And we'll talk about how they're watching in just a moment. But the key thing here is these traits are hardwired. We can't go in and, through training, add new neurons of these types. We can't sort of like just practice at looking for some type of thing until we can have these things pop out. Either it's built into the standard issue human brain or it isn't. And it may be stronger or weaker in individuals, but it's not something that's really changeable. So how's this all happening? Well, this is a visual field. It's actually a bunch of lies about a visual field. I've divided up into a grid to sort of talk about, we've got things looking at each section of the visual field, but it's not really a grid in our real world. It's actually much more of an inverse bullseye with a lot of little things clustered at the center and much bigger things out near the edges. But that's really hard to draw in a paint program. So when we're looking at a scene, in parallel, there's things that are looking for different features of the scene. So for example, we could be looking for things that are running at an angle. We look for edges. A lot of what we're looking at is edges. So, and in this image, we find some of these edges of various types. And it turns out these are actually pretty agnostic to how they're represented. It doesn't matter what color they are in the environment. It doesn't matter kind of if they're big, if they're small. They turn into intensity. So some edges are not very intense. Some edges are really intense and sharp. Different things are looking for edges the other way. Different things are looking for horizontal edges. And this is interesting because you can already start to see a feature of the environment pop out. There's the horizon in this picture. Even though it's kind of weak, it pops out. And edges aren't the only thing we're looking for. Another thing that pops out really easily, as we saw in the examples before, is hue. So here's these intensities of red in this image. And obviously, I've really done a simplified job of this because it would have taken me weeks to actually encode these in any sensible way. But the point I want to make is that while we're doing all of these trait findings, this is all happening in parallel. So we're actually getting something much more like this filtered up from the lowest level of our vision. And the level it's filtering to is still not a conscious one. So this is layers all the way down. But let's start talking through those layers. So we've got the visual field, we take it in, and what we end up getting then is these features. And these features are actually from an artificial visual neural net. So they're what it's actually detecting, which is pretty cool. But some of the features that we end up using are just like circles, these edge lines, curves. And those features end up aggregating. They build up into patterns. So, for example, here we've got the pattern of things that have a vertical grain, which is actually a pattern we recognize really well. Textures are a very easy pattern for us. The pattern of things bundled together, so sort of the beehive pattern or the packed things. And faces, animal faces, human faces, are recognized here at this low level, under conscious awareness. And only then, from the set of patterns that we're seeing, do we end up building up objects. And the interesting thing about the objects that we put in visual working memory is that, again, even though our illusion tells us it's a picture, it's what we're seeing, the objects in visual working memory are a combination of what we see, the properties of the image, and what we already know to be true about those things. So when we look at a flower, we get our own associations. Mine, I have romance, bouquet, spring. You'll have whatever associations you have with flowers. If this particular flower was worn by a relative, a lot, that they used to like to wear one in their shirt, old people still do that, then you'll have association to that person, even though they have nothing to do with flowers. And we can only hold 1 to 3 of these in visual working memory at a time. So we're actually seeing constantly this combination of both what's there and what we know and remember. And we can take advantage of that for our visual processing and for data. But there's still a problem here. So there's one more piece we've got to put in before this makes any sense. Because right now, we've still got an environment where we are totally beholden to whatever is randomly catching our eye in the visual system, where the world tells us where to look, not vice versa. So there's also a problem that comes in where Anne Treisman's experiments had a small replicability problem when they started adding some wrinkles to them. See, I said that she took these people, she sat them down, and she told them they might see a triangle. Well, what happens if you don't tell people what they might see? So is this going to be a line that's misaligned? Is this going to be a different color than the rest? Is this going to be a different shape? I'm not going to tell you. I'm going to do one of these. That was probably pretty fast still. Still pretty fast. These traits are really easy to recognize. But if we had been measuring you, that would have gone from about 1/10 of a second to about 2/10 of a second. And I know that is an eternity, but that is long enough that we're starting to get out of the first layer of the visual system. So we're not actually going ahead of attention now. So pre-attentive might be a bit of a misnomer. What's actually going on here is that these attributes are tunable. So we can take our visual system and we can tell those feature detectors at the bottom level, certain ones of them, I don't care about you very much, be less loud than you normally would. And other ones, if I see anything like this, turn it way up. So if you imagine here, who here has done a Where's Waldo book? So if you're looking through a Where's Waldo book and you want to find Waldo, one of the things you're tuning your visual receptors for is probably horizontal things and red things. So, because he's got a horizontal red stripy shirt. That actually works. If you know that you're looking for something like that, you can give that directive to your visual system and it'll find it. And in fact, you can do that right here, because we've got 3 different things on 3 different traits, and you can read the black blurry letters, you can read the blue sort of pale letters, and you can follow the curve of that red line. And as you're doing it, I want you to pay attention to just notice the other fields kind of seem to fade away just a little. You don't feel like you're going through letters as you're tracing that red line, because in order to trace the red line, because they are kind of right at the edge of being distinguishable from each other, you have to tell your visual system to tune the other ones out. So what we've actually got is that example I gave before is only half of a feedback loop. The other half, the objects we've got in the world, and what we're interested in reinforces the patterns. It weakens some, it strengthens others, which in turn does the same thing to the features. And ultimately, those new strengthenings and weakenings of features change how we direct our gaze. And that's what guides how we see. So a real-world example. Hopefully many of us have shopped for produce. This is a produce section. And just for a quick refresher course, this is what a tomato looks like. We're going to shop for a tomato. But of course, until we have actually looked over the produce aisle, what we see is this, which is kind of hard to take the tomato in. But for most of us, we're going to walk right up there and just go and grab the tomato with no thought about where it is, with no need to go visually scanning over it. Well, why is that? Well, first thing we're doing is we tune our visual system to red because we know tomatoes are red. Then we only have to jump to one place. Look, nope, apples. There we go, it's tomato. And then we do one of the interesting things is we start building up the image from there, but we build it up only around where we need it. So we end up with this sort of focused image. We are only ever really looking at the stuff around the stuff that's important to us, and that's okay, because our brains know that if we cared about something else in the environment, we would jump our eye to it, and before we were capable of having the thought, our eye would already have the data. So we are actually really, really efficient about our use of memory. We don't try to use it for the stuff we don't need it for. So this is a whole process of visual search. And I really wanted to emphasize that we can only do this for the traits that are real, because we are all, I presume, quite literate. We've all been reading a long time. So I've got words on this next slide. In a pile of letters, I've got two words that start with a Q and 2 words that start with a P. And this example will not work because my font has changed. I apologize greatly. Just notice that, because the lineups no longer line up with my words. But you'll notice that actually you can't find either of them super fast. But if they had been where those yellow highlights are, then, which they were supposed to be, then you would have been able to jump your eye straight to those and immediately see them and know you'd seen them, while the words that you hadn't, you'd have to scan for, which you're having to do now for everything. And the reason is that color is one of the traits that our eye actually has that it can tune for, but the shapes of letters, despite how incredibly familiar we are with them, are not. So, habituation does not actually get us what we need. But what's this all got to do with graphs? So Edward Tufte, basically, if you know who Edward Tufte is, he does a lot of really cool stuff with data visualization. That is understatement of the presentation. And he basically said that we should be constructing our analytical graphics to serve the fundamental cognitive tasks in reasoning about evidence. And these first 2 tasks he mentions, describing the data and making comparisons, are the 2 that I'm most focused on, because they're the 2 that I think you can most quickly learn to support with the work you're doing. So let's talk about how we can put all this into practice. So I like to think about those 2 fundamental operations that Tufte talked about in slightly different terms. I like to think about the 2 things that are easiest to do with a chart as being search and compare. So when we search, we basically look at a whole thing and we trust that the things that jump out to our eye are also the things that are interesting in our data. So we are basically we want to make a correspondence between the interestingness of the visual item in front of us and the interestingness of the data. When we compare, what we want to do is put things out in our visual field so that the relationships they have out there in our visual field are the same as the relationships they have in the abstract data. So the other thing that we've got that we're doing whenever we work with data is we have a question of whether we're working with it so that we understand the data or so that we can communicate to others. And I bring this up because you can use the same charts for everything, but the charts you use to understand can be very stripped down. You don't need to add all the scaffolding that explains them. You just need to understand them yourself. Whereas when we communicate, we also need to think about how we're going to add the scaffolding around that helps the person we're communicating to see all of the things that we knew when we put it together. So the first task then, really, as we're doing all this, is to ask the question, what question are we trying to answer with this visualization? So here's the question for analytics 2. I want to find the assignments that are unusually hard or unusually easy, and I want to compare the student's performance on certain assignments to the course average. So we're going to kind of do both of those things. But for what you're doing, so what you're going to do, you're going to need to choose an appropriate chart for your question. And because there is no way I have time to go over all the charts here, I'm just going to tell you about 3 books. Show Me the Numbers is a great book if you are trying to use charts in your work. It's very much a practical book. The Truthful Art is targeted at journalists, but it's also, I think, an excellent book if you are a researcher in any way and need to communicate your work to an unsophisticated audience in your domain, because he talks a lot about how to carry them along that path of sophistication. But if you're like me and just picking a graph a lot of the time, I actually frequently go to Ann K. Emery's website, The Essentials, where she just cataloged all the charts she uses a lot as an information designer, because pretty much every chart I have ever really cared about is on her page, and she talks about when to use them and when not to. And these will all be in the bibliography. So for our system, we chose a dot plot, and we actually chose a bunch of dot plots all lined up next to each other, one per assignment, to sort of create this new hybrid chart that's built out of dot plots. So that's so that we can support this visual search across all assignments while also supporting a comparison within each with that dot plot. So now, once you've chosen your chart, you have to design it. And to ask that question, you need to ask yourself what attributes of the data are important. When we visualize this data, what do we care about? For us, it's assignment averages and specific assignments. Then, what visual feature is going to represent them? So for us, we're using dots and their position. So these are 6 visual features I think that are the most common ones to use. Those books will give you a bunch more, but I couldn't fit them all on a slide. Length, we're really good at comparing relative lengths and figuring out what is longer and what is shorter, particularly when things have a common baseline. Similarly, size, we're very good at doing bigger and smaller. We're not very good at doing how much bigger and how much smaller. Shape, of course, has no real ordinal relationship to it at all. They're just different. So they're great for doing categories. And while we think about hue as having a rainbow order, we don't actually think about it that way in our visual system. So similarly, hue is another non-ordered set. You just want to choose things that are far enough from each other, because hue does have similarity. You can use it to represent things that are similar or less similar, but you can't really get an ordering out of it. Now, brightness, we can do intensity with. We're pretty good at telling whether things are stronger or weaker, but again, not by how much. So when we really want that precision, I left it for last because it's frequently the most common, position. We do 2D positioning really well. That is like our visual system, super good at that. So very frequently, position is the thing you want to go for. So then once you've figured out what you want, the question you want to ask yourself is whether the visual features you're using are distinguishable. Because most of the interesting visualizations, they're not using one thing, they're using a couple. So like, for example, if we're comparing multiple courses and their assignments, we want to be able to tell both what each course's average is and which dot corresponds to which course. Once you've done that for your data set, the next question you need is what supporting information is needed if you're going to be communicating. So what labels do you need on your axes? What do you need to help scaffold the eye to get it where it's going? So let's talk through that over here very quickly. So this is, of course, meant to support a visual search. We've got all these lovely blue dots. And of course, the one that pops out here is that outlier down at the bottom. And we want to find out what that means because we want to get to the data. So we've got this label over here, which are just a little less intense so that they don't compete with the visual search. But then we want to be able to follow it. And we have these really non-intense gray lines to carry the eye across. And they're not intense because we didn't want a grid behind everything interfering with that visual search. So, of course, I've just said a whole bunch of what seem like really wishy-washy things, I think, about the colors and intensities. But I'm going to show you how to do this. So it turns out we did all of this using the HSV color space. So who here's worked with HSV before, or HSB? A couple of people, cool, so hopefully I won't totally misrepresent it for y'all. So turns out every color in this graph is the same shade of blue. So we've got a very, very high saturation, full saturation and very high brightness shade of that blue. Not 100% bright, because at 100% bright, it actually turned out to be too jarring. It was ugly, and that's a great thing with our designer. Then the lines are just the same thing, super desaturated. We've got the dark colors are actually just a very low saturation, very low brightness version. And then when we gray them out to reduce the contrast, that's just us taking it down in saturation. So when we do that and we add a student there, you see they recede and it becomes easier to do the visual search on the student. And since I mentioned that objects are half our memories of them, that's why we used the icons for students, so that they associate to all the other places you've seen that icon in Canvas. So it's a subtle effect. It may only help a little bit of the time, but it helps be consistent if the same image represents the same thing throughout. So here again, we've got that low intensity thing, the student, and you can compare the space between them. It's harder to make a very precise judgment about how far it is between them, but it's easy to get a relative judgment out of that. And then when we start to get into the land of lots of things for sections, here we're starting to have things that want to compete with each other. And again, HSV helped. Now, we've chosen different hues for each of these, but there's the issue of colorblindness to contend with, because a lot of people are colorblind. There's also the issue of not wanting to be carried on just one trait. So you can see they've each got a different shape as well, and we chose the more distinctive shapes earlier, but these are actually all differently placed in HSV space as well. So there we've still got those gray dots, but there's our yellow, our purple, our green, and our black, and you see that they each have a distinct position in HSV space, which is really helpful because it gives us one more thing that we can filter on as we're searching visually, looking for each set. It's one more way that we can tune our visual system. So, to prove this, I used a color blindness simulator to show you what this actually looks like with, first, very common red color blindness. They're less distinct than they were, but they're still quite distinct because they're different in HSV space. And in fact, if we go fully colorblind and simulate a total lack of hue, they're still distinct. They're less distinct. The shape is now carrying more, but we've still got a lot of value from that. And I used, by the way, this color blindness simulator, and again, I'll show it at the end, but it's super useful if you're representing data and want to test that it is going to have good differences in contrast. And for you to do this, this is actually really easy. So if you're using a Mac, this thing on the left is one of the color palettes you can choose. It's not the one with the crayons, sorry. But you can pick a hue and then adjust the saturation and brightness. I like the one with the crayons better. I kind of wish I could do this with it. But with that, you can decide where to place these and make some deliberate decisions. You can draw that little square yourself, right on paper, and just decide, I'm going to try putting some things here. And then in collaboration, we were able to do this in collaboration with design. So it's a conversation between, we think these numbers are distinguishable, these colors are pretty good, if we tuned this a little bit this way, it could increase the distinguishability without making it uglier. So it's always a conversation because the aesthetics part is that judgment call I said I wasn't qualified to make, so I don't make those because I have no gut feels. If you're on Windows, I'm sorry it's not built in because Windows has no standard color picker, weirdly. So there's a tool on the right on the web that you can use that does the same, and you can input it into whatever color picker your application uses. So we've reached the end. Summary, some lessons. So here's what I'm hoping that you guys took away from this, what I took away while putting it together. So charts help us understand our data because they let us use the same mechanisms that we use to see the world around us, which are really well tuned and adapted, and abuse them for our data purposes. And we can tune the human visual system, but only to certain properties, so knowing what those properties are is really helpful. And if we think about the relationship between our data and those properties, we can make our charts way more useful. And finally, if we use color and shape deliberately, that also makes our charts clearer, and it makes them more helpful. So thank you all. So that is the end of the talk, but I do have the bibliography, and I'm happy to answer questions with anything left here. Yep. So if anybody has any questions, I'm happy to answer them before they kick me out.